Okay, today is our problem, the problem of multicollinearity and regression model. The multicollinearity. So here what is happening, how multicollinearity affects any estimated regression line. So that is our guideline that we want to check how the problem of multicollinearity can affect any estimated regression line. And here is our model, right? You can see this is our model, and y is the dependent variable and the rest are independent variable, and it is our model 1.1. You can see from here model 1.1, and we want to estimate this model having 6 independent variables. Okay, but after estimating model 1.1, we saw that only x5 has become significant while others are not. Out of 6 independent variables, only one has become significant and others are not. So I suspect there is a problem of multicollinearity in model 1.1, and that is why most of the variables have become insignificant. Okay, the question is that what is multicollinearity? What is it? If there exists a high correlation between any two independent variables, problem of multicollinearity arises. And multicollinearity makes a significant variable insignificant by increasing its standard error. And if the standard error goes up, t-value goes down, and hence come up with high p-value. So that particular variable becomes insignificant, but in reality it is not. Okay, I'm telling here again what happens actually when there is a problem of multicollinearity. Okay, what is the t statistics? The formula is estimated coefficient divided by standard error, right? Okay, the problem is that what happens when there is a problem of multicollinearity, the standard error goes up. As a result, t statistics goes down. And if the t statistics goes down, then the p-value goes up. And if the p-value goes up, then that particular variable become insignificant all the time. Meaning that I'm telling here all the t statistics, I'm telling again, t statistics, sorry, not t statistics, absolute absolute t statistics and the p-value has always opposite relationship all the time, meaning that if the absolute t value goes up, p value goes down, or if the absolute t value goes down, p value goes up. It always happens. And what is happening here, if there is a problem of multicollinearity that makes the standard error high, as a result t value goes down artificially, as a result p value goes up, so that variable become insignificant. Normally if the p value is more than 5%, that is more than 0.05, then that particular variable become insignificant. So that is the guideline. But what is the multicollinearity is doing? She is making the variable insignificant, but probably that variable is not insignificant, right? Okay. Now, how to detect multicollinearity? So here, how to detect? We run the correlation analysis using all our independent variables given in model 1.1. That means the variables are x1, x2, x3, x4, x5, x6. So we can run the correlation analysis using only independent variable, not dependent variable. Make sure, right? And after estimating the correlation analysis, we find that there exists a high correlation between x3 and x4. That means there exists the highest correlation between x3 and x4, and that is 95.36%. So this one is the highest. The correlation coefficient between x3 and x4 is the highest. So that is why we shall be choosing x3, x4 as a target. So the correlation coefficient x3 and x4 is the target. Why? Because the correlation coefficient is the highest. Here, for this particular case, it is the highest. So now, so as a result, the problem of multicollinearity arises. Now, we have to drop one variable from the model, either x3 and x4, to solve the problem of multicollinearity. Okay, how to solve the problem? That is the second issue. The guideline is we shall drop that variable which has higher p-value out of x3 and x4, right? Because x3 and x4 is the target variable right now because they have the highest correlation coefficient, and out of these two we should drop one variable which has higher p-value. Okay, higher the p-value, lower the level of significance all the time, right? So after estimating model 1.1, we saw that x4 had higher level of p-value, which is 0.30, compared to x3, which is 0.06. So we should drop x4 and run the model 1.1 again. So meaning that we shall be dropping x4 and keep all other independent variable. Why? Because x4 has higher p-value. That means lower level of significant. That means x4 can influence less. X4 can influence y less compared to x3. X3 can influence y more than x4 because x3 has lower level of p-value. Normally, when the p-value goes down, meaning that dependent variable more. So that, and if the p-value is less than 5%, meaning that that variable is significant, significantly explain the dependent variable, which is y. Okay, now after estimating model 1.1, after removing x4, we see that more variables have become insignificant, such as x3, x5, x6. So now you see 3 variables have become significant, but last time only one was significant. Why? Because the problem of multicollinearity has been removed. So 3 variables have been significant. And what is the guideline? Normally, in a good regression model, most of the variables should be significant. So here in our model, 3 are significant out of 5 because we have dropped x4, right? We have dropped x4. So now we have 5 variables, 5 independent variables, and out of 5, 3 are significant, meaning that most of them are significant. So we are happy about the model. Okay, this is our model, and here you can see the what is our problem, how to remove the multicollinearity from the system. That is our whole target that I'm trying to write here. I think it's not working properly. First I check this one, not this one. I have to come down here. Okay, the question is that how to remove the problem of multicollinearity from the model. And you can see from here we have many variables that you can see from here: y, x1, x2, x3, x4, x5, x6. So there are 7 variables, and y is the dependent variable. x1, x2, x3, x4, x5, x6 are independent variables. Okay. Now what I'm doing, I'm opening all the variables. I'm opening all the variables as a group, right? You can see all the variables. I'm opening all the variables as a group. As a group, I'm opening. So now you can see all the variables, right? And see, so these are the variables, right? So from x1, x2, x3, x4, x5, and also xx and x7. Here we have the data. It is only 35 data. You can see 35 data, right? And y is the dependent variable, and the rest are independent variable, right? Y is dependent, and x1, x2, x3, x4, x5, x6 all are independent variable. Now we want to execute the model. So how to estimate model? I go to quick as before, and I estimate the model. I come here, right? First I put y, dependent variable, c, then x1, x2, x3, x4, x5, and also x6, right? Okay, x6, right? We have all the variables. Y is dependent, x1, x2, x3, x4, x5, x6 are independent variables, right? And sample size is 1 to 35, right? Okay, then I press OK. Okay, so this is my result. The dependent variable is y. x1, x2, x3, x4, x5, x6 are independent variable. But here, what is happening? x1, the variable is not significant because the p-value is more than 5%. Here the p-value is 68.39%, which is more than 5%. So x1 is not significant, x2 not significant, x3 also not significant, x4 also not significant. x5 is significant because the probability value is only 0.42%, which is less than 5%. So x5 is significant. What about x6? No, it is not significant because the p-value is 37.05%, and which is more than 5%. So it is not significant. Okay, you can see out of 6 variables, only one is significant. That is x5. So I can assume that, I can suspect that probably in this model the problem of multicollinearity is there. That I assume, right? Probably the problem of multicollinearity is there, and that is why only one variable has become significant, right? Because of the problem of multicollinearity. Okay. Sorry. Now the question is that how to detect the multicollinearity, right? Okay, that is the questions. That is how to detect the multicollinearity. How to detect the multicollinearity in the model. In the model estimated below, right? That is the questions. How to detect the multicollinearity in the model estimated below. Okay, how to detect? So we have to go to the correlation analysis, right? That we have to do to check whether we have to do the correlation analysis to check whether the independent variables are highly correlated or not. And if the independent variables are highly correlated, meaning that there is a problem of multicollinearity. So what is the effect of multicollinearity? Okay, what is the effect? It comes up again. What is the consequence of multicollinearity, right? What is the consequence? Okay, so suppose this multicollinearity makes the standard error big. Okay, the question is that how to get this t value. T value means, suppose I talk about this one. T value means this, the coefficient divided by standard error. I can get the t value all the time, or t statistics. What about this one? This one means 876.42 divided by 3796. So I get this value. This is t statistics. Okay, and what is the t value and p value, and what is their associationship? Okay, normally, not normally, it always happen. The t value and p value always has a negative associationship all the time. If the t value goes up, p value goes down, or absolute t value goes down, p value goes up. So they have always opposite associationship all the time. I said absolute t value, not only t value, meaning that absolute means there is no sign. Absolute means there is no sign, right? All are positive, absolute. So here you see this p value is very small, and that is why the t value is so big, right? You can see from here, right? T is so big, so p is so small, right? So there exists a opposite associationship. And also here, the t value, that means absolute t value, there is no sign, right? That means we should ignore the sign, because I am telling absolute t value. You can see from here the t value is big, 1.92, so p value is small, 0.06, right? So that means the absolute value of this column and this column has a opposite associationship all the time. Okay, now what is happening, what really happens, suppose what is the consequence of multicollinearity? Okay, and if there is a multicollinearity, then the standard error, this one, this value goes up. This value goes up if there is a problem of multicollinearity. This value goes up artificially, right? If there is a problem of multicollinearity, the standard error goes up. And if the standard error goes up, then t value goes down, right? T value goes down. Why? Because this divided by this value actually we can get. So if this one goes up, meaning that this one goes down, and if this one goes down, then p value goes up. And if the p value goes up, that variable becomes non-significant. That variable becomes insignificant. But actually, maybe x2 is a significant, but because of the problem of multicollinearity, it becomes insignificant, right? Okay. And also it is the same story here. x4, if there is a problem of multicollinearity, x4, the standard error goes up. If the standard error goes up artificially, then t statistics goes down. As a result, p value goes up. As a result, that variable cannot become significant in this model. Okay, then comes up how to detect multicollinearity now. How to detect multicollinearity, right? So, how to detect? We have to do the correlation analysis among the independent variable only. Among independent, don't bring dependent variable here. Independent variables, right? Among independent variables only. Don't bring dependent variable, right? Okay, so I have to go to quick, then group statistics, then correlations, right? We have to check correlations. Okay, then I put, okay, here all the variables. I drop y. I can drop y because y is the dependent variable, so I should drop y, and also the constant, the c I should drop also. So these are all independent variables, right? So I run the model. Okay, this is my result of correlation coefficient. Yes, that you can see. This is the result, right? The correlation coefficient. I make it big. Okay, so suppose this one is the correlation coefficient between x1 x2, and suppose I talk about this one is the correlation coefficient between x4 x5 and so on. Okay, now the question is that which one has the highest correlation coefficient from this correlation analysis. So from here I can see that yes, this one, right? This one, meaning that the correlation coefficient between x3 and x4 is the highest. How much? 95.36%. And because of this high correlation coefficient, the problem of multicollinearity has arisen, right? So I'm telling again, because the correlation between x3 and x4 is very high, 95.36%, and that is why the problem of multicollinearity has arisen, and that is why most of the variables have become insignificant. So now, how to solve the problem? Okay, now out of x3 and x4, I must drop one variable. That is the guideline. That is the guideline to solve this problem. Either x3 or x4, that I must drop. But the question is that which one I should drop, x3 or x4. Okay, what is the guideline? The guideline is that out of x3 and x4, which has higher p-value, that one I should drop. I am telling again, out of x3 and x4, which has higher p-value, that I should drop. Okay, what does mean by higher p-value? Higher, I'm writing here, the p-value, lower the level of significance all the time. Lower the level of significance. I'm writing here, higher the p-value, lower the level of significance all the time. So that is the all the time. So now we can check our model that which has higher p-value. Now we can check our estimated model. Now we can check our estimated model that we have just done, that we have just estimated, right? That we can check now, right? Now we can check our estimated model that we have just estimated. Okay, our model is which one? It is here. Model is here. Oh, sorry, the model is here. That we have just yes, this is the model that we have just estimated. Okay, out of x3 and x4, you can see x3 p-value is 0.06 and x4 p-value is 0.30. That means x4 has lower level of significance, because if the p-value goes down, that means the level of significance goes up, and when the p-value goes up, the level of significance goes up, right? So normally if the p-value is less than 5%, meaning that that variable can influence the dependent variable, right? If the p-value is less than 5%, meaning that that variable can influence y. What is y? Dependent variable. That means if the p-value is less than 5%, then that independent variable has a influence on the dependent variable, which is y. So meaning that out of x3, x4, also we can say that in other way, x4 is far away from y. and x3 it is nearer to y because the p-value is small, right? So now we shall drop x4 and we shall estimate the model again. That means what I want to do now, we shall drop x4 and run the model again, right? Okay, so that we shall do now. Okay, I go to quick estimate equation, right? Okay, then I put yc x1, x2, x3, x5, not x4, right? Okay, so this is my new model after dropping x4, right? So now I press OK. You see there is no x4 here, right? So I go to OK. Okay, so this is my new model, and y is the dependent variable, and these are all independent variables, right? You can see from here, and here is no x4. Okay, now you can see x1 it is not significant, right? x2 no, not significant, but x3 yes, it is significant at 4.89%. X3 is significant at 4.89%. That means which is less than 5%. And x5 is significant at 0.05%, which is significant. And x6 is significant at 3.58%, meaning that less than 5%. Now you can see, now the three variables have become significant out of 5 independent variables. Last time only one variable was significant, but now 3 variables have become significant because the problem of multicollinearity has been removed. That is why more independent variables have become significant. And the question is that what is the guideline? Guideline of a good model. The guideline is most of the independent variable should be significant. Then we can say a particular model is a good model. Okay, we have to check how is this model. How is this model that we have just estimated? How is this model from the statistical point of view? How is this model? So model from the statistical, statistical, right? Statistical point of view, right? That we want to check now, right? Okay, first we check, you can see most of the independent variables are significant, x3, x5 and x6 are significant. So the most of the independent variables are significant, so we are happy about it because for a good model most of the independent variable should be significant, and we have it. Then I talk about R square. It is not that high, but at the same time not low also. But the R square should be around 60%, right? So, but here 43.6%. But if the F statistics is significant, so that is the good sign. F statistics, the p value, you can see the F statistics of the p value is 0.37%. So that is highly significant. That means all the independent variables jointly can influence dependent variables. Okay, normally if the R score but F statistics is significant, then we are happy about the model, because R square actually within the sample, the model fit within the sample, and F statistics actually model fit within the population. So normally what I say, if the R square is small but F statistics is significant, then normally I accept the result, right? And here F is significant, so I'm happy about the model, right? Although R square is low. Okay, then I check the residual analysis. I go to view, right? As before, I go to view the residual diagnostic. First I check this one, test of normality. Okay, what is that? This is the Jarkabera statistics, and the probability is how much? 59.75%. So we cannot reject null hypothesis, meaning that the residuals are normally distributed. And the question is that what is our null hypothesis? Residual are normally distributed, and that we cannot reject. So we are happy about this model. And then talk about residual diagnostic, serial correlation, right? That I check. Okay, I keep it to lag 2. I keep it. Proceed. This is Bruce Godfrey LM test. And observed R square is 6.83%. 6.83% means we cannot reject null hypothesis. And what is the null hypothesis? There is no serial correlation, right? And we cannot reject it because observed R square and corresponding p-value is more than 5%. We cannot reject null, meaning that there is no serial correlation. So we are happy about this model. Then I check the last one, the test of heteroscedasticity, that I can check, the last one. Suppose I choose the Bruce-Bregan test, right? That I choose out of many tests. Okay. And here observe test of heteroscedasticity, right? Bruce-Bregan Godfrey. I choose observed R square. Here is 82.3%, meaning that I cannot reject null hypothesis. And what is the null? There is no heteroscedasticity. So this model is good because there is no heteroscedasticity. So the model is good because most of the independent variables are significant, F statistics is significant, and in this model there is no serial correlation, no heteroscedasticity, and the residuals are normally distributed. The only problem that R square is slightly low, but as the F statistics is significant, so the model is all right so far. Thank you very much for being with me for a while. So this is the terms of uses, right, of this model.